Hi, my name is Daniel Blackburn, and this video is about soil water and the basics of water properties that condition water behavior in soils and also water availability to plants. Alright, so this video is part of the SWAE4401 Water and Nutrient Cycling in Soil Plant Environment. This is about basic concepts again. You've probably seen most of these concepts in your introduction to soil and water, but it's worth revising on the perspective of what condition plant growth and water availability to plants. This most of it will be revision for you, but stick on and I hope you can revise those concepts again. So first of all, the structure of water. The structure of water makes that the water molecule. The water molecule will have two hydrogens and one oxygen, and the alignment of these two hydrogen and one oxygen, it's tilted towards one side. This is very important because this makes that the water molecule will have a polar behavior. It means that one side of the molecule will be charged positively with the hydrogens, and the other side of the molecule will be charged negatively. And this makes that you have one positive pole, or maybe two positive poles, and one negative poles on this water molecule. So this makes that the water will interact with other charged molecules, like other water molecules, but also with other chemicals in their ionic forms. It gives the water the property that is a very good solvent for anything that is electrochemically charged. You have some charge in the molecules. This is an illustration of the water molecule interacting with itself, and it forms what we call hydrogen bonds. Hydrogen bonds. The hydrogen makes a chemical bond that is not as strong as a covalent bond, but is strong enough that will align these molecules with each other. So water molecules will be all aligned and held into each other through these hydrogen bonds, and makes them to have a high property of cohesion. So one other property of the water molecules is that it has a very specific freezing and boiling temperatures. Actually, the scale of Celsius is set to match the temperatures in which water are freezing, melting, or becoming water vapor, becoming gaseous, being vaporized. So these freezing, boiling points, they are not a coincidence. They are made to coincide with the water, the temperature in which water changes states. But with regards to the solid and liquid states, there is something very curious about water, is that most of the compounds are, when you heat them up, they become less dense. And when you change them from state that is from liquid to solid, they become more dense. But water has the opposite property. The water, when you freeze it, when it becomes solid, it becomes less dense, and it means that ice can float in water. So this is something that is very important for the distribution of heat throughout water bodies, and this conditions quite a lot of the heat transfer throughout ecosystems also. The cohesion that we were speaking before, the property that the water has to be attracted to itself, to different water molecules attracting other water molecules, gives the water property that the films of water, the interface between water and other substances, gaseous phases, it will have some resistance on this interface. And this resistance is what we call surface tension. You know? So, every film of water in the interface with the atmosphere will have some resistance, and this gives this property that you can resist the breaking of this surface, this interface. The charge of water molecules also gives the property of the water that it will have some adhesion. Adhesion is when the water interacts with solids and surfaces. So this is very important for the water movement in soils, because this capillary effect, uh, uh, it's a function of the size of the pores. If you have, for example, in clay soils where you have very fine pores, you will have more capillarity because you have more surface area in which the water can be attracted to through the adhesion. And then when you have sand soils, you will have that bigger pores, and because of bigger pores, you will have that there is less attraction to this surface, less surface area, less attraction, and less adhesion, and therefore there's less capillarity. This capillarity makes that the water can move in the soil as it moves through a sponge. Yeah, the soil behaves as a sponge, and can retain this water and store this water for the plants. And the capacity of working as a sponge is a function of the size of the pores, and this the phenomena which is regulating this is capillarity and the adhesion of water to the surfaces of the soil pores. Specific heat also is very important as a water property. It is the energy that it takes to change 1 degree Celsius of temperature from the water. The specific heat of liquid water is quite high. So this makes that water can work as a buffer for temperature changes in different environments. And this is also true for soil environments, and makes a nice and stable environment with regards to temperature changes. And this is good for the plants and also good for the microbes in the soil. Heat of vaporization also is very high, and this heat of vaporization can be explained to this next chart, which shows in the y-axis temperature, and in the x-axis heat added. If you come from point A, which is frozen water, and you start adding heat, you will reach 0 degrees, and by the time you reach 0 degrees, if you add more heat, it will not change the temperature. There is some resistance here for changing the state from solid to liquid, for melting the water. The distance between B and C is showing the amount of heat that you need to add to change status from solid to liquid. And if you figure out here that from C to D on the x-axis, this is the amount of energy that you need to add to change the water from 0 degrees to 100 degrees. So you can see here that it's almost the same amount of energy that you have to add to change the water from solid to liquid, and then you have to bring you need to apply the same amount of energy to bring the water from 0 degrees to 100 degrees. But if you now look of the energy that you need to apply to change the water from D to E, it means to bring the water from liquid at 100 degrees to vapor at 100 degrees, it's much, much higher. It's nearly 5 times the amount of heat that you need to add to heat to change the temperature of water from 0 to 100 degrees. So this heat of vaporization, it's also a very important property of water that means that it will maintain water in this liquid state for a longer period of time, and therefore work as a solvent on these environments. So when we talk about solutions in the water working as a solvent, we need to make an important distinction. There are some things that are in water, they are not dissolved in water, they're suspended in water. And the way that you can tell this suspension and solution apart is if you centrifuge this suspension and you have a phase separation, it means that these particles were not actually dissolved on the water. They're not in ionic form interacting with the water molecules. They were actually in their molecular form, but suspended in very fine molecules or very fine clumps of molecules or aggregates that can be suspended on the water. But if you centrifuge, you can separate, and this is what we call suspension. And if you centrifuge and you cannot separate, this is a solution. The ions that plants absorb, that plants can uptake from the soil solution, these are dissolved ions, not suspended ions. You need these ions to be on their ionic form in order for plants to have access and uptake those nutrients. So you have the solute and you have a solvent. The solute will be the ions, and the solvent will be the water itself. And this is a figure representing this dissolution of sodium chloride on water. It means that if you have a salt, a precipitated salt, this salt will start interacting with the water molecules and become coated with the water molecules. The water molecules will align with the charges of these molecules and let them be integrating this solution in a very fine way that cannot be separated by centrifuging. Whereas if you have a suspension, like for example clays in water, these clays, if you centrifuge them, you can still separate. So these clays, they are big enough or aggregated enough that they can phase separate when you centrifuge. This is how we tell apart a solution from a suspension. So one of the important properties of water that we're going to talk about more when we talk about soil chemistry is that water can dissociate. The water molecule, the hydrogen and the hydroxyl the hydroxide base on the water and the hydrogen can dissociate. So about 1 in every 10 million water molecules dissociate into H plus and OH. It means that water will have a concentration of H plus naturally dissociated on the water. And this concentration of H plus is what we call the pH. The pH of a solution is the concentration of H plus. And because of this, the water can have a quite wide range of pHs, and naturally the pH of water, neutral pH of water, if you don't have any impurities, water will have a concentration of H plus that will be represented as pH 7. So water in soils will be part of a bigger system, and water will be a part of the soil pores. The soil pores, actually this is not the correct image for this. The water will be part of the soil pores. The soil pores can be filled either with water or air or both, and the water behavior and availability to plants is conditioned by how much water and how much air you have on these pores. If you have all the pores filled with water, this water is highly available to plants, and even gravity can move this water through the soil profile. If you have that the soil is very dry, you still have water hygroscopic water on the surface of the solids, but it could be that this water is retained with too much energy and it's not available to plants. So most of the time we need the solids to be in an intermediate state where you have part of the pores filled with water, part of the pores filled with air. So we defined the availability of water to plants based on the potential, the water potentials that represent these states in which the water can move on the soil. If you saturate the soil, you have a maximum water retention on the soil, a maximum water possible to be added to the soil is saturation. If you leave gravity to act, gravity will remove some of this water, and what is left on the soil after the removal of gravitational water is what we call the field capacity. And if the soil continues drying to the point where the water becomes unavailable to plants, this is what we call permanent wilting point. Yeah? And the difference between the moisture content that you have at field capacity and the moisture that you have at permanent wilting point, this is what we call available water. Okay, available water. The field capacity represents the moisture that you can find when the potentials of the soil are at minus 0.33 bars. And the permanent wilting point is represented by the moisture that you can find in the soil when the soil matrix potentials are at minus 15 bars. So if you think about this system, but now if you look at one soil particle, not at a full system, you can observe why the potentials of water changes with the distance from the soil surface. So you have the soil particle in the soil pore, and the water molecules that are very close to this soil particle, they're tightly held by the soil particle. So they're held with high energy, yeah? Too much energy that the plants cannot remove this water. So there is this difference between the water that is too close to the soil surface that the plants cannot remove this water. Then you have the water that is too far away from the plant that even is so loose, it's held with so little energy that even gravity can remove. So between the saturation and the moisture content in which the water cannot be retained even by the capillarity, this is the water, the gravitational water, the water that can be removed by gravity. In between this field capacity, the moisture that is left when the gravitational water is removed, and the point where the moisture in which the plants cannot remove that water anymore, the permanent wilting point, this water is what we call available water for plants. And you can see that this available water for plants can be represented to how close are they to the surface of the soil particles. So again, 0.33 bars is the water which is at a distance which the gravity cannot remove this water anymore. 15 bars, minus 15 bars here, is a permanent wilting point. It's at a point which the plants cannot take water from the soil anymore. But you also have that there are other limits below that what the water can the water that the plant cannot take. Below this limit, still there are other concepts that are important. The capillary water is the water that can move through the soil through the effect of capillarity. And some of this water that is retained below the point in which the plants can uptake are still mobile in the soil. And there is a point where you have water that's so tightly retained that they will not move well with capillarity anymore. This is what we call hygroscopic water. Between the air-dried soil and the oven-dry soil, there is some amount of water which is called hygroscopic water. Yeah? So we have the concepts of gravitational water that can be removed by gravity, the difference between the gravitational water moisture content and the moisture content at minimum in which the plants can uptake water. This is plant available water. And we have capillary water between air-dried soil and field capacity, and hygroscopic water will be between air-dried soil and oven-dried soils. Yeah? Of course, we are interested in the water which is available for plants, and we have that the finer the pores, you will have more available water. The field capacity, as you decrease the size of the pores, field capacity goes up. Permanent wilting point will also go up, but at a lower, slope. Yeah, so the increase is less steep than you see on field capacity, and that means that when you are decreasing the amount of the size of the pores, you increase the surface area, and you have more available water on the soils. Okay, you have more available water on the soils. So these are the important concepts that you have to remember: hygroscopic water, capillary water, gravitational water, wilting point, permanent wilting point, field capacity, and plant available water. These are the things that you must remember from this lecture, and these are the concepts that you will need to remember to also to discuss the results from the lab that you will see from plant available water. Last but not least, when we move from water availability to plants, we have to start thinking about water as a vehicle for nutrients. Yeah? The soil is a soil solid matrix behaves as a reservoir of nutrients. The plants will take the nutrients from the soil solution. So it means that when the roots take nutrients from the soil solution, then the soil solid phase will replenish the solution with nutrients, and so on and so forth. There is an interplay between what is the plants are taken from solution and the capacity of the solid phase to resupply that solution with the nutrients. So this is more on the soil chemistry, and we will talk about this on the next lecture. What is the interplay between the properties of the soil as a solid matrix, the soil solution, and the availability of nutrients to plants on this system. So this is what I had to bring for you today. I hope you enjoyed and learned some. And next video, we will talk more about soil chemistry.